So I am Valerio Mariani. I'm a staff scientist in the lab of Henry Chapman in Hamburg. And I would like to thank the organizer for allowing me to present some part of what we do there. And specifically, you will see that, at least in the first part, HDF5 will not play a big role, but it will come in at the end. Just be aware that this is a very specific use case, but there are people doing these kind of things. So what we do in the lab of Henry Chapman is serial crystallography. So crystals come in a liquid flow continuously, and they get hit over and over again by the X-ray pulses. Every time there's a pattern which is created and read from a detector. We do this with liquid jets, so where the crystals come in a liquid jet, but also we do this on tape, so the crystals are deposited on tape and the tape rolls and gets hit by the X-rays, and also on chips. So the chips move and the beam enters at the point where the crystal is. Now, when we do this kind of experiments, sometimes we need to take decisions which need to be taken within seconds. For example, are we hitting the sample? In the first case, we need to move. Is the injector clogged? We see if the injector is clogged, no crystals come, say, in the liquid flow, and then we need to stop the experiment, fix, and start again. Or did the injector the liquid jet move? Sometimes it fluctuates a little bit, and we need to be able to move so that the beam is aligned with it. Also, are these crystals on the chip that we are hitting? Or are there saturated pixels that could damage the detector? Now, for this kind of decisions, accuracy is not a strong requirement. So we want to know, are we hitting a crystal or not? Not are we getting 21 or 22% hit rate, right? Low latency is also a requirement. And it's more important than completeness. If I compute the hit rate on, say, 20% of the data we collect, it's still accurate enough for this kind of decision. If the injector is clogged, we will see the hit rate going quickly to 0, and then we know the experiment needs to be stopped. So to work on these things, we developed ONDA, which stands for Online Data Analysis, which is an online monitor which tries to give up-to-date information for real-time human feedback. The idea is that it keeps up with the data flow. So it always processes fresh data. As I said, speed is very important. Completeness and accuracy are relatively secondary. Now, I know that several facilities have already tools for things like this where people can monitor their experiment in real time. Now, the problem for us is that we do sometimes these kind of experiments at many facilities. And so we have to go, and every time we have to learn new tools. Additionally, the tools that you develop are probably used for several experiments, for several kinds of experiments. And so they probably show us a lot more information than what we need in our specific case. Because of this, one of the guidelines of developing ONDA was, you see it at the end, portability and flexibility. We need to be able to tailor the monitor to a specific experiment, and we want to run the same kind of monitor everywhere so that wherever we go, it looks always the same. We also have had our goals in developing ONDA, so to keep the design as minimalistic as possible. That's the principle of keep it simple, stupid. So for example, we don't redevelop algorithms that have been optimized. We just, when possible, link to outside libraries or outside algorithms, and we try to develop as little as new things as possible. So we are not to fall in the not invented here syndrome. We also want to be intrinsic parallelizable. And at the end, what we want to offer is, yes, a set of framework with a set of modules to develop new monitors, but also a set of prepackaged monitors that you can start using right away. So we use a parallelization architecture, which consists in several workers which get data from a facility, and I'll come back to this later, which reduce the data, so process, for example, a single image, extract some information from that image, for example, for crystallography, the breakpicks, and send only the reduced information to a master, which computes all the statistics that need to be computed over more than one image or more than one event. The data can also be streamed out to a GUI, for example, for visualization, which is usually what happens, or even printed to the console. So currently, the workers and the master talk to each other using MPI, And the GUI sends, the master sends the data to the GUI using a ZNQ socket. But all of this is abstracted away, so this might change in the future. Now, ONDA is a structure in layers. There are three main layers. The parallelization layer extracts the parallelization part, so in this case MPI is the least important, let's say, well, the least interesting. The two interesting ones are the data retrieval layer and the processing layer. So the data retrieval layer has this task. So if we are at a certain facility, say at Petra 3, where we use Hydra to, this program developed by Manuela Kuhn, Daisy, to retrieve the data, probably the data comes from a Pilatus detector, and the detector distance might be a setting that someone put in a configuration file. Now, this is shown in the processing layer as just entries in a Python dictionary. Now, if we move to another location, for example, LCLS, where the detector is a completely different one, and the detector distance is a readout from an encoder, the data retrieval layer makes sure that this is shown exactly in the same way to the processing layer. So in a way, you don't have to care where the data comes from and what it looks like. It's always shown to you in the same way. Of course, this is not magic. This is usually taken care of by the core developers, whatever that term means, which is the people who are familiar with the code. Usually, the way to retrieve the data in real time is facility independent. And so what we do is we go to the facilities, we go there maybe sometimes days before the experiment, and we work with the people there to retrieve the data. The idea is to turn facility dependent data formats into facility independent abstractions. And then people can only work at the parallelization layer, and they just have to write two things. One function, process data, which is executed on the workers every time data is retrieved from a facility. And another, collect data, which is executed on the master where data is received from the workers. Just a very quick example, this function could look like this. So process data contains this Python dictionary that exposes the data extracted from the facility. Suppose that you have a pig finder, you can find the pigs. You put it in a dictionary, you return that dictionary. You don't have to care how it is transferred because the parallelization layer takes care that this is sent to the master node. Where this function, just again an example, the data that you return from the previous function in the worker appears here in the collect data function on the master. And then you can do also whatever you want. For example, you can add it to a peak accumulator and compute the maximum resolution that you have, which is an information that needs to be computed over all the data collected until now, and then you can send it to a graphical interface. But enough with the theory. It was said in a meeting that people running the experiments don't care about all of this. This is nice, but this is all architecture. What they want to do is run the experiment. So the first thing they have to do in the configuration file, they just specify which layers are used, and if they move, for example, if they want to run the same crystallography problem at Petra 3 or LCLS, all they need to do is change this, and someone coded the data retrieval layer that allows them to run the crystallography layer everywhere. So this is an example of currently this is the only monitors that we ship together with ONDA, but several more are in development. You will see an example later. This is the one with a view for crystallography. As you can see, the information is minimal, right? So we have a virtual power pattern on the left, the heat rate on the top right, and the saturation rate on the top left. Sometimes, for example, using chips, there are some crystallization phenomena that cause very bright peaks that can damage the detector, and so we want to immediately see this and stop the experiment or attenuate the beam. Sometimes people want to see the images, and this is an example of the image collected last week at the European XFEL. As you could see, we are not eating anything. Now, once we saw this working, we started getting taken with it, and we developed internally, at least we made public a lot of different monitors. This is another of the experiments that get done in our group. So this is an experiment where a molecule, so there are molecular beams, so there are molecules flowing in a beam. They get oriented by an optical laser. And then they get hit by the X-rays. The idea is that when these molecules are destroyed by the X-rays, the ions that are at the top and at the bottom of the ring, in the molecule, will explode, let's say, away from the molecule in this direction, right? So the more the molecules are aligned, the more we should see some very tight clouds of ions at the top and at the bottom. And then we could monitor the experiment, again using ONDA. You see on the left the cloud of ions as shown on the VMI detector, and on the right the calculated alignment score. And the delay was low enough, 1-2 seconds, as you can see, that people could literally tweak the knobs of the X-ray laser and optimize the alignment. We also had different monitors developed for the scattering of fibers, where you can see total intensity over time on some of the panels. This is also monitors that we developed internally for now for multi-layer lenses experiment. Here we do scans, and some of these scans can take hours. So it's important to us that we know, are we at the right spot? Are we in focus? And if we can stop in the middle, we literally save hours for our experiment, right? Another monitor, well, I think you got the idea, right? We can develop very specific monitor for very specific experiments showing exactly what you need. This is for fluctuation X-ray scattering, being developed by Canupria Pandey at Berkeley. And currently you can use ONDA using PSR, so you can use it as LEC, using Manuela Kunz Hydra at Petra, but it's facility independent. I'll come back to it. And you can use it from files, HDF files and Nexus, CBS from the Pilatus detector. In the future, you'll be able to use it also the European XFEL. Work is underway to port it there. We support a lot of detectors. There's no need to go to the laundry list, just to give you an idea that most of the detectors that are used for this kind of experiment are supported. Not only X-ray detectors, but also VMI detectors and digitizers, cameras. And in the future, we want to add even more detectors, more features, for example, strict masking for crystallography. We would like to run ONDA at scale on clusters, and we heard this morning about Kubernetes. We are trying to see if we can run this at scale with thousands of nodes and at more facilities. For example, ESRF is not supported yet, as you can see. Now, where does HDF5 come into play here? So first of all, everywhere, because we try to, in ONDA, to use only standards which are well-defined and well-documented. So HDF5 is the standard format for all the kind of masks, all the kind of files that we read. But there's also another important detail which leads to a very specific use case. We get the data in real time, possibly before it's written in the file system, because sometimes we have to wait minutes for that, right? So in some facility, we get it through some different technical solution, like reading from the shared memory of the computer managing the detector, or from the DAQ. But in other cases, we have the detector which writes simply HDF5 files on a computer called the detector server, which is connected to the detector server and especially solved with the detector itself. So meaning we have not much control on this. The files are transferred to the file system, for example, at Petra 3 at DESY, by this program called Hydra, which just looks for the files as they appear, and as they are ready, as they are closed, they get moved to the file system. And then, basically, Hydra is a multiplexer, meaning it can send the data to different locations. And so we thought, well, Hydra sees all the files, knows which ones are the most recent ones, so we'll just ask Hydra, can you please stream us the file over the network, so we don't have to go to saving them and reading them somewhere. And of course, this comes the problem, right? Because currently, so Hydra is file content agnostic, just read the files and said, here's a binary blob. I don't know what it is because I don't care, let's say, about the experiment. Is the binary content, do what you need with it. Now with CBF files, we can read from the stream, but with HDF files, of course, the library currently has no function to read from a stream. Although I heard this morning it's now possible to write plugins, so I didn't know before. So probably we already found some kind of solution. So currently what we do is we say to Hydra, at least tell us where the last file is. And then we go and read it ourselves. But then it gets tricky because the computer where ONDA is running needs a very fast connection with the file system where the files are and so on. Or another thing that we try to do, at the beginning, what it was quite clumsy is to get the binary from Hydra, dump it into a file in a random disk, and then read it using the HDF5 library. And of course, the other problem, but this is mitigated by Swimmer, is that the files, at least at the beginning, need to be closed before it's even transferred. Now, the problem is that many of these detectors come with this computer which cannot be updated, right? And they sometimes have old versions of the software, in particular of HDF5, so sometimes we can't take advantage of this. So this is what I wanted to tell you about, this very specific use case, which has these strange requirements, but I thought you might be interested in this. So this is work done mostly in the lab of Harry Chapman at DESY, but by many, so here Thomas White, Anton, Alexandra, Andrew, and Jochen all contributed code, ideas, and support. But also Manuela Kuhn, in addition to coding Hydra, also helped us to coding ONDA, and there are collaboration with Buffalo, with Berkeley, and with several people as LEC. Yeah, and so there's a paper out, this, and the releases can be found at this website. Thank you.
Thank you so much. Are there any questions? We have 4 minutes for questions.
I just wanted to mention that at the bottom of your list there was Chris O'Grady, and he's one of the people who was kind of a sponsor for our new work on the swimmer, on the single rider, multiple reader. So it's very exciting to see that this possible application would be of value to you.
Yeah, maybe he was thinking exactly about a case like this.
Yes, he was, yeah.
Thank you. Unfortunately, there is a problem, so we need to talk to vendors so they update software.
Yeah.
So they can take advantage, for example, from splitter and mirror directives.
Valerio Mariani, it's great talk. Nice, very great presentation. And I really like the way you approach the adaptation of your program to the local specification of the file. You know, there are constantly these ideas, like Nexus, for instance, to create files that have a common structure, common among laboratories. And there are other ideas to implement these kind of ideas. What are your thoughts about it?
So, in general, my personal belief is that homogeneity, in the sense of using the same software or the same format everywhere, is too big of a challenge. Let's put it like this. I try to strive for interoperability, right? So, for me, the ideal situation is not that you use a format, a specific format that I need or want, but that I can come to your facility and read some specification and talk to you and work on making it compatible. And so interoperability, I think it's at this stage an achievable target more than homogeneity.
May I ask you a question? Thanks for the presentation. I was wondering about vendors, and I mentioned the fact that there are vendors and they need to communicate with them. I think that Detectors is implementing a streaming interface, and the fact that Detectors is implementing a streaming interface, I wonder if there should be different way of outputting the data, and if HDF5 is really it's a good format for getting data out of the detector, because HDF5 is more an archival format than something for treating data live. So I'd like to have your thoughts on that.
So for my kind of application, I would agree with you. For me, I mean, if you stream binary data, or as long as I know the size or how the data is organized, for me, that's enough. But we must also think about the other people who do other processing with the data, right? So eventually, I think that for the permanent output, HDF5 is big enough of a standard that it's supported by pretty much everything. So yes, for this kind of application, maybe other different type of streaming might be okay. I just brought this to the attention of the people here because this is the de facto situation. So many detectors just write HDF5 at this point, and this is what we have to work with currently. But I know, for example, the EIGER detector can stream data.
Have you already experienced with this?
So we had the same experience at the beginning. And at the beginning, it was not really working well, but I'm talking about 2 or 3 years ago. I heard that recently things got much, much better. And we will be working in the future exactly on this, especially with the idea of running on that scale, because the data that comes out of the EIGER is really a lot, even for an MPI scheme like this.
Thank you. Thank you very much.